You're welcome to the first talk of the morning session. So each talk is going to be 55 minutes plus 5 minutes for your questions, and there's going to be a 10-minute break between the talks. So the first speaker today is Rupert Frank from University of Munich. He is an expert in analysis, mathematical physics, and spectral theory, and he will talk on the liquid drop model. Please enjoy.
Thank you very much. Thanks to the organizers and to the program committee that allowed me to give this talk here about the liquid drop problem. Thanks for you for showing up, and let me say immediately, please interrupt me if things are unclear, right? So I don't need to go to the end of the talk. It's more important that I explain things well, and so if there are any questions, please let me know. Okay. So I'm trying to give an overview over this liquid drop model, which has been around in the physics literature for some 100 years or so, but only in the last 10 years it became relevant for, or mathematicians have started to look at it. I'm trying to pick two topics that, well, I think are reasonably easy to present and where there are also open questions that I would like to present to you. And so therefore the talk is divided into two rather independent pieces. The first one is the standard liquid drop model in its original form that Gamow had. And then the second talk in an application of that liquid drop model to astrophysics. All right. Mathematically, the first one is related to some sort of isoperimetric problem that is open. And the second one to the question about proving pattern formation for a certain particular problem. So let's go into details. This is a graph that I hope you remember from high school physics. That's the binding energy per nucleon. Okay, so down here we have the nucleon number. I should say that in this talk I do not distinguish between neutrons and protons. So for me, there is sort of a pre-decided fraction of particles in the nucleus, and a certain fraction of them happens to be protons, the other fraction happens to be neutrons, and that fraction is sort of fixed. And I'm just talking about nucleons as these particles. Okay. And so we have here the elements hydrogen, helium, lithium, beryllium, and so on. And what you see is, as I said here on this axis, this curve is the binding energy per nucleon. And what you see is this curve goes up, reaches a certain maximum at a certain iron isotope, and then goes down. And of course, that's the division between nuclear fusion and nuclear fission, right? So if you're on the left side, when the energy is increasing, you gain energy by fuse nuclei together. If you fuse two hydrogens into helium, you gain energy. That's when you go up. From helium, you gain energy to get to lithium. On the other side of this maximum, well, that's nuclear fission. There you want to break the nuclei apart. Okay, that's, so this is uranium, and sort of that's the other side. Okay, and so, well, this was the this is the picture that I hope we all know. And now there have been several models, mathematical models, to explain that. And I start with a very, very basic model. This was introduced by Gamow some 100 years ago. And I mean, there are many more complicated, more involved, and more realistic models of this. But this model that I'm going to present has the advantages that it's very simple and it explains qualitatively this picture. And it's easy to look at, to discuss mathematically. And so this is what I would like to focus on. And I should say that virtually every textbook on nuclear physics that you open still has this model in. So even though it's old, that's sort of the first thing you learn when you learn about nuclei. Okay, and so what was Gamow's idea? Well, Gamow's idea said, well, a nucleus, that's just some subset of R3. Any set of R3 can be a nucleus. And then the measure of that set, we call the nucleon number. Of course, I should say that we ignore units. You know, there is, I mean, really, it's just what I should say. The number is proportional to that measure, but I set these units all to 1. Okay, so the measure of the set, that's the nucleon number. Okay, and then given now any possible shape that we have, we want to define the energy. And what's the energy? Well, there is the perimeter and there's the Coulomb repulsion. So the perimeter, that's just if you set a reasonable nice boundary, then this is just the surface area, nothing more than that. Now there is a notion, for those of you who are familiar with this, of the perimeter. There you can define the generalized notion of the surface area for any measurable set. It's like in the sense of distributions or something. But just think surface area, okay? So this tells us that this nucleus wants to stay together. It would cost energy to split apart. Now the second term, that's the Coulomb repulsion. There we remember that at least part of these nucleons are actually protons, and these protons repel each other. So actually they don't want to be too close together. And so what we have is just they repel each other through Coulomb forces. So that's just the double integral over omega of 1 over x minus y, where x and y are sort of the positions of these nucleons. Okay, so that's a very simple model. Again, there would be constants here in front that I've all scaled to 1 to make the problem look nice. But when you really want to look at such graphs, you have to introduce, of course, all these units. Anyway, so that's the energy functional, and then the ground state energy. So what should decide the shape of the nucleus. Let's minimize this energy functional under a given number of nucleons. Okay, just minimize this functional under measure constraint. And if you want to read about the history, there is some, well, now in 2017, there's a review article by Choksi, Muratov, and Topaloglu in the notices of the AMS. And in particular, you see many mathematical questions left over. Okay, so yes, please. Well, we think of sort of as the perimeter of omega as like the kinetic energy, right? Because it discourages very rough boundaries. It wants to have sort of makes it smooth or makes it nice. Very, very good. But of course, I mean, you have a very good point. So one of the questions that is, I mean, left to mathematical physicists is sort of to derive that from first principles. To really think there was at some point a real kinetic energy of a real operator, and why do we get this at the end? And in particular, one of the modeling assumptions that is used there is that these nuclei have a constant density, that nuclear matter has constant density, that there is no variation. And that is something that has to be justified. And there are many other questions that are that one can ask about this. I will focus here in the first part only on this minimization problem, because I think that's reasonably nice to explain. So once again, our functional, the perimeter, and the Coulomb repulsion, we want to make that as small as possible under measure constraint. And the two competing terms that we have is the perimeter that wants the set to be connected. And actually, if we think a little bit more quantitatively, what is if we ignore that term, what is the problem of minimizing the perimeter given the volume? Well, that's a classical isoperimetric problem that wants us exactly to have a ball. And we can do the other thing. We can look at the Coulomb energy, right? So first of all, if we minimize, so the Coulomb energy wants the set to spread apart, right? The particles repel each other, so they should go out of each other's way. And actually, there's a theorem of Ries that says that being a ball is the worst for that. Okay, so the ball is the minimum of this, and it's the maximum of that under measure constraint. So they really want opposite things. And so if you look at the functional who wins, who is the minimizer? And so the answer depends on A, on how much mass you put in, because sort of you see already this is like scaled like a length squared. This scales like a length to the power 5. So at small lengths, the perimeter is dominant, right? Because you have the length cubed is fixed. So the length squared is dominant for small lengths. The length to the power 5 is dominant for large lengths. Okay. Now there is something that I'd like to call the no compromise conjecture. And the no compromise conjecture says that there is a fixed value. Below that value, the perimeter has it its way, meaning it makes the set a ball, and above that value, this term has it its way, so it completely spreads things apart, so there is no minimizer. Okay, so I'm calling this the no compromise conjecture because it's not that these two terms can find some compromise arranging it. Say you say agreeing to be an ellipse, right? Then the ellipse, it's not exactly a ball, but it's not exactly completely spread out either. The conjecture is that this does not happen. Either it's a ball or there is no minimizer. Okay, now that conjecture is not a conjecture in the physics textbooks. If you look at the physics textbook, that's just a fact because nuclei are around. I mean, that's written there. So there's no question about this, and this is virtually every book that you look at. In the mathematical literature, I think it is stated for the first time by Choksi-Pelletier that this is something, that should be proved. Anyway, now when one believes that conjecture, one can easily compute that value because what is sort of the critical thing that can happen? Well, you have to compare the energy of one ball with the energy of two balls of equal radius but infinitely far apart, right? Because that's when it splits it apart, this is what happens. And when you do this, you come to certain formulas which has square roots of 3 and so on, third roots of 2, and the value that we perhaps might want to keep in mind is 3.5 because that will play the role. Okay, so below this value 3.5, we want to be a ball. Above, there should be no minimizer. That's the task to prove. That is an open problem. Now let me tell you what is known. And so therefore, what is known, there are two results, 1 and 2, that go in the two directions. And this, you see, they start with there exists. The one result is when A is very small, then you are a ball. Okay, that can be shown. I should say that this argument, or the arguments that I know or that existed until a year ago, they were all via compactness. And that does not make us really happy because there's a smaller nucleus, that's hydrogen. And if we can't say anything about hydrogen, then we don't care. It's a void result. Anyway, so, but things have changed and I will talk about that. That was one of the first applications of this isoperimetric inequality in quantitative form. If you heard these developments, Fusco, Macci, Bertelli were among the first, and then it has been a big development. Now, on the other side, there's a result saying when A is very large, larger than some constant, then there is no minimizer of this problem. Okay, that was, I think, for the first time proved by Knupf and Muratov, and simultaneously independently by Liu and Otto. Okay, now they had an argument that is quantitative. They did not use compactness, but the techniques that they were using did not really allow to track the value, what it is. And so the question, and that will be the rest of the slide here, is what can we say about quantitative results? Because remember, the number that we have in mind is 3.5. How close can we get to 3.5? This talk for several years now, and I try to encourage this problem because it's really nice in my opinion, and I will show you this argument. I've encouraged people to do this. At one of these talks, Otis Chodos was a participant, and then 5 or 7 years later, he wrote me an email, I have a result now, and then he sent me this paper, and it's a beautiful result. They could push the fact that you are a ball up to 1, right? I mean, this is a concrete number, and it is only like a factor 3.5 of the optimal result. So that's the first and the best result that we have. And I hope very much that 7 years from now, I will receive an email from one of you who sort of improves the results one way or the other. All right? Yes, please. Oh, everything is in 3 dimensions. Sorry, yes. No, it's a, you make a very good point. All this can be formulated in general dimensions. You can even replace the Coulomb potential different things. This has also been studied in part. The results are less precise than in this case, but here for this talk, I want to focus on that. But thanks, you're absolutely right. Now here is the result on the other side that we proved with Ron Killip and Nam some, I mean, might be almost 10 years ago now. What we could do is on the other side, we could say that we could make the second part quantitative. We could say if A is greater than 8, then there is no minimizer. Okay, so again, compare 8 to 3.5. Well, we're still away, but you know, it's a number. And one thing that makes me sort of happy is that 8 is already in the physically realistic regime. Because when, so what I did not say in the previous slide is the fact that this picture ends on the right, that's not an artifact that they want to end the picture, but it's actually something that the model says that there is a largest nucleus, right? Okay, which is one of these radioactive elements. And in the units that I'm using, this happens at 10. Okay, so there are these radioactive nuclei which sort of are stable, but not really forever. And so in these units, this is 10, where you here on the right side, and sort of this result says, I mean, it's a question of interpreting sort of what it means to be a radioactive, but sort of the point is that this 8 is smaller than 10, and this means that up to 10, the 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 ball is still locally stable. So if you do a second variation analysis, the ball is stable up to 10, but it's no longer a minimizer, at least starting from 8. Okay, so that's an interesting feature, and that has physical consequences. Anyway, let me say it again. The question is to improve that, get closer to 3.5. But what I want to do now in the next few minutes, I want to present you a proof of this 8. Because that proof is, I hope, understandable. And, you know, it's strange that it has not been improved in these past years, although it's, I mean, people have tried. So let me take, this is my minimizer. Let me pretend that my minimizer looks like that. Okay, and so what I want to remember what I want to prove. I want to prove that the measure of this set is less than 8. All right. What I'm going to do is I'm going to pick a hyperplane. The hyperplane is described by a vector nu, and sort of if you have a certain point, which if this is the origin, then the distance from the origin. Let me call that t. Okay, so I mean, this means just I'm taking a hyperplane and cutting the set into 2 parts. Okay, so I have now a left and a right. And what I can do is I can compute my energy. Well, this is the original energy I have. And now let me do this. This is the energy, and let me just write here left and the energy of the right. And so what I think I'm doing is I'm cutting the set into 2 pieces, and then I'm moving the pieces away from each other. Okay, so I have now a disjoint, a trial set that has 2 components very far from each other. And I'm using that trial set to plug it into the energy. Now, of course, my original set is a minimizer, so this is smaller than that. And now if I move the 2 things apart, you see what happens is that the interaction between the left and the right, which are very far apart, is negligible as I move them to infinity. Okay, so I have this inequality between the energies of the original set and the 2 pieces that I've cut out. All right, so let's look at how this reads. What does it say? Well, what is the change that happened? Well, of course, sort of the surface area, I still have the original surface area. But now I've introduced, by doing this cut, I've introduced this additional surface area. So this is, so let's say this is twice because it appears once from the left and once from the right, the surface area of this cut. So this is x dot nu equal to t. Right? That's where the set intersects the hyperplane. All right. That's what I have to pay. But of course, I've also gained something because before, well, the left was interacting with the left, that we still have. The right was interacting with the right, that we still have. But originally, the left has interacted with the right, but that has disappeared when the two things were infinitely far apart. So therefore, what we have is the interaction. So let me write here the characteristic function, x dot nu less than t. That's when x is on the left. And y dot nu, that's the other particle on the right. That's what this says, dx dy. Do you understand? Because all the other terms cancel. And so this is the interaction that is on the left, but is not on the right. Okay, so this inequality I get, because omega is a minimizer, I have that inequality and I have it for every nu and I have it for every t. So what am I going to do? Well, I'm going to integrate with respect to t. Right? Because I don't know where to place my hyperplane. So I'm just sliding it this way and that way. And then you see what comes out of this integral. Well, if you compute this measure here, this two-dimensional measure here, and you slide it around, then what you get is just twice the area. That's Fubini's theorem or something. Okay? And now on the left side, when you integrate t, well, you get what you get. It's the integral omega omega, and now you get nu dot y minus x, positive part, divided by x minus y, divided by x minus y dx dy. That's the integral that we get, right? By integrating with respect to t. And now we can do one more thing. We can average over the orientation of the hyperplane. See, that is independent of the rotation. And here you see when you do the averaging, well, you see, I mean, whatever it will be proportional to that vector here. Okay? And so when you do the math, then you get 1 over 4. And then you get, so there's a numerical constant, but then you get the length of the vector, which is just the length of y minus x, well, divided by x minus y, so that cancels. So that just gives you the double integral of omega, which is omega squared less or equal than 2 omega, and that says that omega is less or equal than 8. Okay? And so that is the argument that we used there. That's what got us to 8. And so my question to you, can you do better? You know, I mean, if the set is the ball, as we believe, then, I mean, you made a big mistake here when you cut into pieces. So one should be able to do better. But, you know, I don't know how to get to, it would be great if one could get to 6 or 5, I don't know. So this is an open problem, and please think about it and tell me about your updates. Okay, so that concludes the first part of my talk. This was this isoparametric problem with that comes from the liquid drop model. Now I'm going on, and I want to talk about an application of this thing in astrophysics. And let me go immediately to the pictures. Okay, so there will still be a liquid drop model, believe me, but here's the physical picture that we try to understand. Look at this picture down there. So we're looking now at a neutron star. Okay, and so this is the outer crust of the neutron star, and we're going towards the inside. This is towards the core of the neutron star. Okay, and so what you have there is essentially a sea of electrons. So the electrons are no longer really bound to certain nuclei, but they're all over the place. And then in this, you have sort of droplets of nuclear matter. And what's described here, what's in red, are the electrons. So that's the C, that's everywhere. And then you have these droplets of nuclear matter there in blue. And what you see is, so the volume fraction, the further you go in, the less electrons you have. Out there you have only electrons, sort of. In there you have very few electrons. And what you see is that you have sort of a phase transition. Phase transition meaning when you're out here, you have the nuclear matter forms essentially balls. And these balls are arranged on a three-dimensional lattice. You go further in, then these sort of ball-like shapes become bigger and bigger. And then there's a critical value. And at that critical value, what you get instead is long extended rods. And these rods themselves arrange themselves on a two-dimensional lattice. Okay, so when you look at these rods from above, you see a two-dimensional lattice. And then when you continue further, at some other critical values, these rods become long slabs. Okay, so like two-dimensional sheets that have a very small thickness. And again, they arrange themselves periodically in one dimension. So there's a periodic spacing of these sheets. This formation has the beautiful name. Physicists are very good in giving names. These are the nuclear pasta phases. Because we start with the gnocchis, we go to the spaghetti, and then we come to the lasagna. Okay, I'm not making this up. Go to Wikipedia and Google nuclear pasta phases. It's a very well established picture. Nobody has seen this, I should say. But people have, well, these are neutron stars after all. But people have models, and they have simple models and they have complicated models and everything in between. And this has been confirmed by various numerical computations in these models, very complicated simulations, Monte Carlo and whatever, nuclear dynamics, molecular dynamics. Anyway, so these are the pictures that we would like to explain. This is sort of pattern formation. We would say that we would like to see in a simple model like this that we do have such a structure, such phase transitions. Okay. Now I have to say, this is a big open problem proving appearance of crystals, of periodic structures in mathematical physics. That's one of the biggest problems there is. And so this has been around for centuries, and we know very, very little. So we have to be modest with what we want to do. And so what I will explain to you is something that happens sort of here in the outer crust, where we are in this very dilute regime, where we have very many electrons and very few nuclei. And that's what I'm going to describe here. So let's go back one slide. Here is the liquid drop model with background. Okay, so let me perhaps clean the board and make a new picture. And the one thing that's important is sort of to understand the length scales here. So these neutron stars, they are several kilometers big. And even if you look at just the outer crust, then this is still several kilometers. So that's our big set. We call it lambda L, but this is really huge. Okay, and what we have inside is of the size of an atomic nucleus. Right? These are many orders of magnitude smaller. Okay, and so what we look, okay, and so I should say that everywhere here in this whole universe that we have, there's this soup of electrons. And this has a relative density rho. And inside we have these droplets. Okay, let me draw them. Of course, I can draw them only way too large. So this is my omega. My omega consists of several components. All this together This is all omega, right? They all look the same because I cannot draw a different shape. Sorry. Okay, so anyway, so this is all my omega. This is the nuclear matter, and this is the electronic matter in the background. Okay, now what does our functional have? Our functional has a surface area term. That's still the same we have before. So here for the surface of the nuclear matter, we have to pay. Then when you look at the double integral, there is the omega omega term. That is repulsion between the protons. That's the same that we know from before. Then we have the rho rho term. That's repulsion of the electrons, right? The background with itself. And then there's a new term where the electrons interact with the protons. That's the mixed term, the omega times rho term. Okay, that is because sort of the background attracts the nucleons. All right, and so the new game is to minimize this. All right, but actually, as I said, we're not so much interested in the precise minimization of this because this is huge and we don't really care what happens at the very end of the star where some strange things could happen. So what one does in physics is one first takes what is called the thermodynamic limit. So meaning I'll take this, I compute the energy, I think I can compute the energy of this thing, and I divide by the volume of this big box. And then my first task is to prove that this limit exists. Okay, that I mean is not completely trivial because I mean you have 1 over x interactions, and you should think 1 over x is not integrable. It's actually far from integrable, right? 1 over x squared is still not integrable. 1 over x cubed is still not integrable. So you're missing several orders of magnitude, which means that if there's a small defect here, small change, it affects everything everywhere. That's a long range nature of Coulomb, which makes life complicated. But it can be done. Lieb and Leibowitz and Lieb and Naunhofer have done things like that in the 70s. Their methods apply. Alberti, Ciocci, Otto have proved this thing exactly for this and have even shown how much this, I mean, at a fixed L differs from its limit, and they proved a sharp rate. Anyway, at the end of the day, we get a number E of rho, which is the energy per unit volume, okay? And it depends on rho, which I remind you is the coefficient before the background. So that's sort of the volume ratio between nucleons and electrons. And so we are in the regime where there are very few electrons, so rho goes to 0. And I would like to tell you about what happens in the limit E rho goes going to 0. And so let's move on. So this is the part, this is rho going to 0. This here is rho equal to 1/2 when you have these lasagna sheets, and actually everything is symmetric, it repeats itself as you go towards rho equal to 1 is the opposite side here. Okay, now here's the theorem. It's a new theorem. It's not on the archive yet, but I hope it will be by the end of the week. We've just finished the last things in this write-up. What we get here is a 2-term asymptotic of this energy. Okay, so it scales linearly with rho. Then there's a term of order rho to the 4/3, and then there's a small remainder. And what I will tell you, of course, is what mu star is, what E star is, and what these numbers mean. And what I want to convey to you is understanding these numbers means understanding this gnocchi phase on the previous picture. Okay. Before telling you what these things are, let me emphasize that it's really important that we first take L to infinity and then we take rho to 0. That's a physical thing, right? Because you want to think you're really inside this nuclear matter. This thing is kilometers long, this direction, and this is the size of an atomic nucleus. Okay, so it's really a huge distance of length, and one must be very careful about this. But this, of course, makes the problem mathematically harder. There have been results before where rho was coupled to L, and where people got the first term. And if you're very, very dilute, so that there are only 3 or 5 nuclei in the universe, then they got something that resembles that term. This was due to Choksi-Pelletier and Knupfer-Muratov-Navarga. All right. And in this physical regime, the first term was done in joint work with Lukas Emmert and Tobias Koenig some years ago. But yes, please. Okay, so that's exactly so. Let me defer the answer to that question because that's, of course, the crucial point. And that's, I will tell you this about when I tell you what the coefficients are. Is an, yes. Well, but the relative density, not talking about the density, but the relative density. The relative density between electrons and protons, I mean, I hope I convey this in this picture here. It's almost all red. So I'm here sort of on the outside. Yes, exactly. No, not the red, but the blue. The density of the blue, there are very few blue things here. So I might have said it the wrong way. So there are very few, excuse me, very few blue things out here. And yes, you're right, yeah. You're getting me confused now. It's a relative density. No, it might, right. Think of it as the density of the neutrons. Yes. Yes, right. So you want to have the whole thing neutral. I see what you say. Well, um, I see your point. I see your point. So there is, it's not something that is in the picture, I guess is my question. But you need to impose a sort of a global neutrality. See what I didn't say, should have said it here. So the whole thing only works when the system is neutral. So you think there are, okay, you're really getting into the precise modeling. There are different kinds of electrons, those that just mediate the neutrality. Okay, and then there are other ones that really that are available to move. Okay, and we're just so I mean, if the system is not neutral, then there will be huge forces, and everything will just go to the boundary. That sort of that. Then there is no. Um, so I discard those electrons that make it neutral. Okay. Those need to be there just in order to have anything. It's just the excess electrons, I should have said. Thank you. Thank you for clarifying this. Good. All right. So now, right. So what I have to tell you, okay, what I perhaps want to first is what these two terms mean. Okay. So the first thing is that these things, they don't look like that. They certainly don't look like long things, but they look like small balls. This is what we want to show, right? Now the size of these balls, that is order 1, and the distance between them, that's order rho minus. It's a mean particle spacing. Okay, this is these are the nucleons. And now when I say that we have this energy with this term mu star rho, what I mean is that we can describe the shape of each individual droplet. And when I say that we can get the energy to order rho to the 4/3, what I want to say is really that I can understand the relative distance of the droplets. Okay, so in other words, the mu star corresponds to the shape of these things, and the E star corresponds to their arrangement. And I'm coming to your question soon. But let me describe the mu star. No, other way. The mu star is our old friend. Mu star is just this iron isotope up there. That's the element with the largest or smallest binding energy per nucleon. Okay, mu, here it is, E of A divided by A. I put minus because I like to think of energies as being negative. You have to flip the picture around. I mean, that corresponds to this thing. Okay, and so you look at this, and this you call mu star, and that's our first coefficient. Having the energy correct to that order means that these droplets are made of the guys that optimize this. That such sets exist was shown in joint work with Lieb, and there is also another paper around the same time by Knüpfer, Muratov, and Varga. The open conjecture, I remind you, is that these sets are balls. We don't know that, and our proof would certainly be much easier if we knew that these were balls, because when they can be any shape, essentially, and then then they might have a dipole or a quadrupole moment, which has a big effect on the other things. So that makes the proof complicated that we don't know it. But the point is, we don't need to know that conjecture. Now let me go on. Let me tell you what the E star is. Here's the E star. This is what's called the Gellium model. The Gellium model was introduced by Wigner in 1934. This is a model for classical point particles. Okay, so X consists of capital N numbers in R3, or points in R3. These points repel each other through Coulomb forces. And then, same thing, they are attracted by a background, here of density 1, and the background repels itself. So that's just a constant. You don't need to care about this. And then, among these point configurations, so these are just points now. Points. Let me perhaps draw another picture over there, right? So these are just points. Again, you have the background. You associate a certain energy to that. You enforce neutrality so that you have exactly as many points as background charge, and then you prove the existence of the thermodynamic limit. That was done by Lieb and Nadenhofer. Again, it's not completely trivial because of the long-range forces. It had been an open problem, but they managed to do it some 50 years ago. And then you have this. And now again, we do not know. This is another big open problem, one of the biggest, I think, in all of mathematical physics. Describe these minimizers. For this simple problem, take the thermodynamic limit, ask yourselves, how do these points arrange themselves? What everybody believes is that they arrange themselves on a body-centered cubic lattice. This is an open problem since 1934. Okay, so you might have heard about these developments in dimension 8 and dimension 24, where people could find a lattice that minimizes that is universally optimal for all kinds of optimization problems. Dimension 3 is different. Dimension 3, you have two good candidates, the BCC and the FCC lattice. And it can be either one, this one or that one. And the numbers are very, very close. And actually, it's, I think, in the third part in 100, that the BCC and the FCC lattice are different. But by now, I think people believe that it must be BCC for that. But even before that, the question is, do these points really arrange themselves on a lattice? And once they arrange themselves on a lattice, then you can compute among all lattices which lattice it is. Anyway, so that's another big conjecture. And if you want to read more about this, I refer to you to the review by Mathieu Levine. And also after Lieb's seminal works on this topic, recently Silvia Serfati and collaborators have studied these problems and variations thereof. Now coming back to my constants, remember I still want to define for you what this constant E star is. Well, here it is. The E star is essentially this gallium energy, and then multiplied by sort of the mass, you know, that's sort of the A's. Oops. The A that corresponds to this ion. Okay, that's the fact it multiplies with. Okay, and so the physical picture we have in mind is if in the gallium model the nuclei arrange themselves in this BCC lattice as is expected, then these droplets down there arrange themselves in the same lattice. But again, I want to emphasize this is an open conjecture and our result is valid independently of that conjecture. So you can think of it sort of as a conditional result, or we just say that this is somebody else's problem. We say whatever happens in gallium happens there. You can say it's that the gallium model is sort of a universality class and that we are in that universality class without knowing what exactly happens in that class. Okay, and so I think that's an important point of view, sort of to distinguish the level of the problems. Right, one problem is to prove this, but this should be proved in the simplest possible model there, and then it should be proved separately, sort of what happens in these more complicated models. And so I think this is one of the insights in our paper, that we can do this without knowing what happens here. Again, if we would know that this is the BCC lattice, our proof would be much easier. But we can do it without knowing that. And now I think I'm getting towards the end of my talk. Let me spend a few minutes here on the case of dimension 1 and 2. So you can ask for similar questions, right? Now in dimension 1 and 2, you would replace the 1 over x in the functional by the corresponding Green's function. So you would take minus x, minus absolute x in one dimension, and you would take logarithm of 1 over x in 2 dimensions. And you would ask exactly the same questions. So in 1 dimension, it turns out that you can compute this E of rho explicitly. There's a beautiful formula here. It is. There you know everything you want to know. Okay, that's simply what it is. In 2 dimensions, well, we can get the first term, but we cannot get the second term. So the proof of this theorem that I described to you really relies on the fact that we are 3-dimensional. There's an open problem here. Try to do the same thing in 2 dimensions. Okay, of course, sort of there is a 2-dimensional gallium model, and for the 2-dimensional gallium model, there's a clear conjecture. It's perhaps easier, closer within reach than in 3 dimensions, because in 2 dimensions we believe that there's a canonical lattice that the particles should arrange themselves on. But we have not been able to do this. There have been partial results in some coupled limits, and as I said here, there's a first term. What I want to emphasize, and that's important, the other way around. In our main theorem, the energy goes to 0 linearly with respect to rho. And then what we get in before is sort of this ion, you know, the largest guy in this picture. That does not happen in dimension 1 and 2. In dimension 1 and 2, there is no liquid drop model, there is no ion or something, right? So look at this. This goes to 0 like rho to the 2/3. This goes to 0 like rho log rho to some power. Okay, and that is because this E, the analog, the liquid drop, go back to the beginning of my talk. If you write this liquid drop functional in 1 or 2 dimensions, the energy is just minus infinity. Okay, and so therefore you cannot have a first term that goes like mu star, or put differently, you cannot have size 1. In dimensions 1 and 2, these droplets are smaller. They have a disappearing size in the limits, and that changes all the scales. So there's really something going on. And yes, and here's the picture. Going back to the nuclear pasta, this is one of the very first papers on this from 1984. You see here, these are the gnocchis, the pastas, the lasagna. Okay, and what you see drawn here is the energy of the sphere. That's what we've computed. It's this line that goes up here. You see the energy of the cylinders, that's conjectured energy in 2 dimensions. And then you see the energy in 1 dimension. Here the units are made so that this is flat, but this is really the thing I showed you, the explicit computation. It's this thing here. Right? And now what they say is to prove the idea of where this nuclear pasta picture comes from is you just take the infimum between the 3-dimensional energy, the 2-dimensional energy, and the 1-dimensional energy. And sort of here down there, this is what I call rho. There are certain values of rho where the 2-dimensional energy becomes better than this energy of these gnocchis. Okay, and this describes these phase transitions. Okay, so it's the minimum of these 3 curves. Anyway, this is at this point speculations. I mean, I just want to show you this is how this is explained in the physics literature. There are certainly, you can read this as many conjectures, and there's lots of things to do. Let me summarize what I told you in this talk. So we're getting to the end. We have discussed the liquid drop model in 2 different flavors, once without background, once with background. Without background, we've seen this isoperimetric problem where it would really be nice to say something. And this is both because it's a nice geometric problem, but it also because it appears in more complicated models, like for instance, this model with background, you know, where in this limit we see these iron nuclei. Okay, then in this, continuing with this model that's used in astrophysics, the key question is to prove the existence of these phase transitions. We could at least establish on energetic grounds that there is this gnocchi phase, which consists of nuclei of size 1 that are ordered rho to the minus 1/3 from each other. If these conjectures are valid, the size 1 shapes are just balls. The arrangement is on the BCC lattice, but this is our result does not shed any light on these conjectures. It's just that we can separate these difficulties, and I want to advertise these big problems. I mean, this is of course a huge major problem, open problem, where many people have worked on. But it's good even to emphasize such big open problems. And I think that's all I wanted to tell you. Thank you very much for your attention.
Thank you. Are there any questions from the audience?
Please. Mhm. Um, okay, yeah, no. So I wanted to, right. So here I wrote a minus in order to make E star positive. And then I put another minus because EJ is negative. Right, exactly. So, I mean, perhaps I should not have done it. Okay, right. So the gallium energy is negative, so there is a net attraction. So these points I mean, after all, they attract themselves. There's a lot of cancellation, big cancellation, but they attract each other to form a lattice. So therefore, the energy is minus. Okay, it's negative. Thank you. Yes.
Do we know any local minimum instead of global minimum of that you have mentioned?
Okay, very, very good question. So this was one at, I was thinking for a long time about how to do this talk. This concerns the ground state. Now, in these these applications, actually what might even, for some question, might even be more important than this ground state is the first excited state, so to say. So it's what I believe to be a min-max critical value, the first min-max value. And when you look at the first paper, so there's a first paper by Bohr and Wheeler from 1939, and they make pictures, they drawings, how they believe it works. I mean, of course, they don't use the word min-max critical point, but I think that's what it is, and they study this in great detail. And then even, I mean, before 1945, there are a number of people really investigated this. These were in part classified papers. They really tried to understand these deformations, the critical points. The second, so it's the first excited states, the min-max. So that it has many open questions. I had one paper where I started to construct a bifurcation branch, but what continues with a branch is unclear at the moment. And so I'm happy to give you more references if you ask me afterwards. Okay, so that's something important. Let me say now one more word here about this. Even there are excited state solutions. Even there people have, you can think of so this is closely related to what's known as CMC surfaces, constant mean curvature surfaces, right? Because after all, the perimeter is what gives you the CMC, and you can and people have constructed very crazy CMC surfaces, and so you can think of perturbations of those, and those have been studied even in this astrophysics model in the physics literature. I don't know about the applicability, but I've seen, these papers, I've seen these pictures, and they are quite amazing. Yes. So again, these are things where mathematicians certainly can have problems to play with and guidance from the physics literature. Thank you.
Any other questions? Okay, if not, let's thank the speaker again.